the Gibbs free energy. In this video, I'm going to connect the Gibbs free energy with the equilibrium constant. And this is really thinking about the Gibbs free energy under non-standard conditions. Gibbs free energy shows up on our third exam. And as we think about equations or resources that would be provided for the student, well, just this idea that we do quite a few calculations involving the products minus reactants. That might even be involving the enthalpy, the entropy, the Gibbs free energy. So this isn't really a provided equation, but many times with provided data, that's how we set up the calculation. We have an expression here involving the Gibbs free energy, the enthalpy, the entropy, and the temperature. And we want to be able to interpret the signs for each of those. Recognize that the value equals 0 when we're at equilibrium. And given that information, we could calculate the temperature for a phase change. We could calculate the temperature at which a process becomes spontaneous or it stops becoming spontaneous. These next two expressions right here haven't really come to those yet. What are those used for? These are ones that would allow us to connect the Gibbs free energy under standard conditions with the equilibrium constant and to consider the Gibbs free energy under non-standard conditions. So we want to be able to convert between the equilibrium constant and the Gibbs free energy under standard conditions. Given non-standard conditions, modify the Gibbs free energy using Q and explain conceptually how the Gibbs free energy is different when we have standard and non-standard conditions. So this whole overview here on non-standard conditions, the information I'm going to share within this video here, I first want to tell you about my treatment of how it appears in Chemistry 1220. Share some evidence that this is a conceptually difficult topic for the students. Like you need supporting information for that, but I'll point out a really key misconception that students have. I'll share with you a lab that you might want to use and briefly discuss a few possible ways to improve student understanding for this topic. So when I'm thinking about spontaneity and the equilibrium constant within my textbook and within most other general chemistry textbooks, this is a pretty standard treatment, meaning kinetics are introduced, there's aspects of equilibrium, and then the thermodynamics section is found. So let's recognize that within this storyline, and I think within your own understanding, you already have some insights about equilibrium. When we're looking at the equilibrium constant, we could look at the concentrations that we have in that moment, which have the expression Q, or we could think about the ones that are present when we're at equilibrium, which is K. So when we're looking at equilibrium, we are doing comparisons between Q and K. When they're equal to each other, that means we're at equilibrium. When they're not equal, it's giving us information about the direction with which the reaction will take place. It's telling us about the spontaneity. So even though this was something that we introduced when we were looking at equilibrium, it's in the same language here whether something is spontaneous or not. This is another way of saying that the concentration is going to affect the spontaneity. So that's something that we need to begin to account for. For a particular temperature, our equilibrium constant is a constant. We saw when we looked at or thinking about it in terms of kinetics, there's a temperature dependence on that. But for a particular temperature, the equilibrium constant is a constant. But the relative concentration of the reactants and products, by varying those, we can describe whether the reaction is spontaneous in the forward direction, spontaneous in the reverse, or is at equilibrium. This expression is beginning to bring together those ideas. Delta G naught, let's remember, that's describing standard conditions. The solutions would have a 1 molar concentration, gases would be at 1 atm. So if we're thinking about this expression, this is really important for us. You could say that information about the Gibbs free energy under standard conditions, you might say, well, that's extremely useful. You can make that case because it allows apples to apples comparisons. We're taking everything and say, let's consider it the same way. Same concentrations, same amounts present. That's useful to know. But you could also turn it around and say it's not useful at all. It's, after all, the Gibbs free energy under standard conditions It only works for those exact concentrations. And even if we put together the lab where we start with those exact concentrations, those exact amounts, they're going to change as the reaction proceeds. So you might say, well, it's useless. What's the point? You've given me information about something that's really never going to exist. The Gibbs free energy under non-standard conditions, now that becomes powerful in a different way. In order to get that, we're going to begin with information describing the standard conditions, and then we'll adjust it for the amounts of the reactants and products that are present, because that's what the Q tells us. So this is a really important idea, how we can take the expression for standard conditions and modify it for what we're probably actually going to encounter. Conceptually here, this is a really important idea. Teacher to teacher, this is central to understanding spontaneity and the effect of concentration. So the Gibbs free energy under standard conditions is related to our K value. You could look up tabulated values for both of those. At equilibrium, Q is equal to K. At equilibrium, the Gibbs free energy is equal to 0. I'm not saying the Gibbs free energy under standard conditions. I'm saying the Gibbs free energy that we have reached is equal to 0. There's not a tendency to go in either direction. So if we manipulate that just a little bit, we could set the Gibbs free energy equal to 0, and we find that we have a way for solving for now the Gibbs free energy under standard conditions, connecting that to the equilibrium constant. Looking at this relationship then, there's a relationship between the Gibbs free energy under standard conditions and the equilibrium constant. We can do the math for those. So typically with my students, I have a couple different ones for them to calculate, find the missing values within here, and notice what we have. When it's a very positive Gibbs free energy for the standard conditions, it's a really, really small K value. When it's quite negative, it's a really large K value. So conceptually, what is this telling us? Is if a process has data for a Gibbs free energy under standard conditions, it has a K value. And when I say it has data, if it conceivably has data, if we can conceivably think about whether it's spontaneous or not spontaneous, it's going to have a K value. When we say something goes to completion, we would say that it has a very large K value. It would have a very negative standard Gibbs free energy. This is really a way of thinking about conceptually, everything can be at equilibrium, right? Everything, it could have a really, really large K value, a really, really small K value, but it's going to have a K value for it if it has this value for the Gibbs free energy. So conceptually, this changes things around. I'm not saying that that always takes place. We don't want to confuse our description here with kinetics. We don't want to say it's necessarily taking place even at a measurable amount, but it's conceivably everything that we're looking at to some extent involves equilibrium. Now, this placement right here, this comes after equilibrium within my course. So we're sort of back to this case, teacher to teacher. What comes first? Do you want the phenomena or the explanation? It's useful within my book where we're looking at the phenomena first, and then we can begin to explain it when we add this tool to our tool belt here. If we place it first within here, you'd have to work a lot more to begin to establish what we even mean by equilibrium. I think there's advantages here if we do it in sort of a iterative way. We can explore phenomena involving equilibrium, but there'll be times where we say, okay, we really can't explain that yet. But let's see what the phenomena is, and then eventually we'll have tools to explain it. Those tools, they appear once we have descriptions involving thermodynamics. Then it allows us to revisit those earlier ones. What are your thoughts on this? What do you think as far as having Gibbs free energy as a tool to explain things? Do you like this iterative process? Do you like to do it and then come back to it? Where we cycle back? Do you think it should take place and be found first? Only afterwards? What are you thinking? So if we play it out here and think about what does this mean in terms of the direction. This is a slide where I know I go too quickly through. I share my thoughts on it, but there's a lot for the students to really digest. So first of all, I'm trying to contrast what does it mean to say the Gibbs free energy has a negative value, and if I'm looking at it under non-standard versus standard conditions. When it's negative for non-standard, that means as what we have right there in the beaker, that's a spontaneous reaction in the forward direction. If it's listed there involving standard states, that means it's spontaneous in the forward direction when these are the concentrations or the amounts. When they're at 0, we've reached equilibrium. The first case would be equilibrium for the conditions that we have, whatever they are in the beaker. The second would be equilibrium when they are in their standard states. Now, I can think of many, many examples where delta G equals 0, right? If I know values where it's at equilibrium, I am telling you when delta G equals 0. However, I can think of no example where delta G naught equals 0. Consider how unique this is. This would be to say you've put together a reaction, and it just turns out that it is at equilibrium when every single concentration or amount is 1. Really? Have we ever seen that? I've never seen that, right? I've never seen a case where my equilibrium constant is 1. I've never seen a case where the standard Gibbs free energy has a value of 0. But I have so many examples, right, where we have it where the non-standard one has a value of 0. To me, that's really an important distinction. Last thought is, what if it's not? What if these are not negative? Well, if they're positive, very insightful too. They just told us that the reverse reaction is spontaneous. Here's a example. I'm going to work through a couple examples where I connect this back to things that we know about solubility. So this is one from the e-text. I'm going to first look at it this way. This is something that we would have been calculating involving solubility. So let's say we have this general salt and we're calculating the molar solubility. We would set it up, solve for x, and in this case, if this is the KSP value, we could see that it has a very small molar solubility. If we're thinking about what does that mean in terms of the delta G naught then, we can plug it into this expression and we find that it has this very large positive value. So what happens if I add the salt to the water? It's very insoluble, but some of it dissolves. It's going to dissolve until it reaches a molar solubility of this value. It's not going to reach the standard conditions. That's what this positive value is telling me. It is not going to reach the standard conditions. It is non-spontaneous in terms of reaching the standard conditions. But does some of it dissolve? Indeed, some of it dissolves. We look at a few implications or play it out here a little bit now looking at calcium hydroxide. And you're going to see why I think calcium hydroxide is an important example. So we connect it first of all back to other things that we've been doing. Let's calculate the molar solubility and the pH for that solution. Let's calculate what delta G naught would be. Positive value is telling me that I do not reach the standard conditions. I do not reach 1 molar concentrations. What changes within this if we add H+? This is thinking back to how we can affect the shift the equilibrium here. I'm not changing the value that I would look up within the table for the delta G naught, but I'm changing what's actually in the beaker. I'm changing the delta G. Looking at other features right here, I'm trying to look at the relationship more between Q and K. What happens if those change? If I'm looking at a different Q, I'm looking at how I can change delta G. Another way to practice it, let's put in these particular values and calculate delta G. We could find under these, the forward reaction is not spontaneous, but the reverse is. The reverse would mean that it's forming a precipitate. So here I'm trying to connect the language of delta G naught, and aspects of solubility. How about within this example? This is one that I believe was taken from the Mastering Chemistry homework system. What happens to delta G when I'm changing the partial pressure of H2? So I'm seeing right here how I can change the delta G. So I'm connecting this back to aspects of Le Chatelier. And so I'm cycling it back to try to connect what happens there to see how when we make a change, we're changing the amounts, Q is changing, and so we're finding that our delta G is changing. Couple end of chapter problems to have folks practice with. Now, this one right here, that was sort of my treatment when I put it in 1220. What are your thoughts right here? I know that I'm trying to connect it back to things that we would have seen involving solubility. What are your thoughts as far as the Gibbs free energy under non-standard conditions? Now, when I say that I have evidence that this is a difficult conceptual topic for students, this is what I mean. So there's this experiment here that's in the Journal of Chemical Education. Determination of KSP and these different quantities, thermodynamic quantities, by looking at the dissolution of calcium hydroxide. This is an experiment that we did for several years at OSU. So we saw this as an experiment that was listed. We gave it a try. So I've managed this in labs with hundreds of students. So it has some interesting ideas. This is something you might want to consider. So first of all, the topics that it includes, I think are important ones. Equilibrium, the free energy, enthalpy, entropy, all of those are important topics, I think. It's a pretty easy lab to do. Doesn't have any fancy chemicals involved. It's a simple titration, and within that titration, you're going to be able to calculate these different quantities. Let me show you what goes on. So first of all, the idea here is you have a saturated calcium hydroxide solution, and you can determine the amount of hydroxide that's in the solution by using an acid-base titration. So right there, good application, right? Acid-base neutralization reaction in order to determine the amount of hydroxide that you have in solution. If you know the amount of hydroxide, you can calculate the KSP. It was a saturated solution, so you take the molar solubility and you calculate the KSP. Now, if you know the KSP, you can calculate the delta G naught at that particular temperature. Just plug it in order to do that. So that's pretty cool. You've now taken your titration and you've calculated this thermodynamic quantity. Now, it gets cooler here. Do this experiment at two different temperatures. Do it at room temperature and do it for a saturated solution at 100 degrees C. Use each of these KSP values to calculate the corresponding Gibbs free energy at that temperature. You now have two expressions with two variables, delta H naught and delta S naught. So this is a way, two equations, two unknowns. You can use that temperature dependence to solve for these. So how cool is this? So simply by doing two different titrations, you can get all of the thermodynamic quantities for it. They share how this is typical data, and we get pretty typical data on this one too. Typical meaning it's pretty close to what you would find reported, and it's definitely functional. So there's a KSP value at around room temperature and a KSP value around 100 degrees. It points out that calcium hydroxide is unusual in that it's more soluble at the lower temperature than at the higher temperature. And as the author notes, this gives an opening for thought-provoking student discussions. Goes on to say, okay, if we use the KSP values, these would be the delta G naught values. Let's put that together with two equations, two unknowns, and solve for the change in enthalpy and the change in entropy. So when I say two equations, two unknowns, this is what I'm talking about. You've got a Gibbs free energy, and you've got an unknown as far as the enthalpy change and an unknown for the entropy change. And you have that at two different temperatures. So here I show how you can go through and solve for what the change in entropy would be. Plug it back in, and you get the change for the enthalpy. Pretty cool way to get at those. Now, we did that several years, and we eventually ran into trouble because we asked the students, well, what's going on? They could do the experiment, they could come up with the values, but first of all, this was conceptually difficult for them. What does it mean when you add the calcium hydroxide and the entropy goes down? I'm not saying it's impossible for them to comprehend that, but this was something that was, I won't say distressing, but it was unclear to them what was going on there. We also then began to ask this question, and when I say we, I began to ask this question in lab. Well, delta G naught is positive. What does that mean? And students would say, well, that means the process is not spontaneous. It won't take place. The calcium hydroxide will not dissolve. Now, I found this distressing. They had just done a titration to determine the concentration. They had just done an experiment to tell me what was the concentration of ions in solution. But then they look at this positive value and they say there will not be any ions in solution. This mismatch right here, in part, led us to stop including this lab because we were not able to really, in that space, have a rich discussion to explain and explore what was going on. What was going on is the calcium hydroxide, it dissolves, but it does not reach the standard conditions of 1 molar concentration. That's what a Gibbs free energy under standard conditions is telling us. Are we able to reach those standard conditions or not? So I think this is a really good lab to begin to probe this idea, but you need to pair it with the corresponding discussion. Now, as far as possible ways to improve it, what do you think? Do you have any suggestions for that? How might you take it up? One suggestion for you. This is what I've had the most success with. Following our discussion of thermodynamics, we look at electrochemistry. Included in that is the Nernst equation. Notice how the Nernst equation is really just another retelling of what we did for the Gibbs free energy under non-standard conditions. We have something that would be tabulated under standard conditions. We are now saying, well, if you change the amounts there, what would be the actual potential? Students, I find, are so much more capable of understanding this expression than they are understanding our one involving the Gibbs free energy. With this kind of setup, when I do it as a demonstration, instead of a light bulb, I usually have a little fan that spins around. But when I pose a question, will this cell operate forever? Can I put it together and have it just keep running? Will the fan continue to spin? And everyone will say, no, the battery is going to run down. That's an experience they're all familiar with. The battery running down, well, what does that mean? If we come back here, it's not changing the tabulated value, but it is saying that the amounts that you have are changing, and the thing that counts is the resulting potential. That's the same kind of concept that I'm trying to get across when I'm looking at standard and non-standard conditions for the Gibbs free energy. This idea of having a functioning cell within here, students really get this part. They really struggle with the Gibbs free energy, but with this feature, it really works for them. So my suggestion for you, it comes back to this idea of, well, what do you cycle back to? Having looked at this aspect of the Nernst equation, I think it allows us to cycle back and revisit non-standard conditions. When I first get to non-standard conditions in chapter 19, I don't care how slow I go with it and how much we explore it, it just doesn't make sense. But as soon as I bring up this feature right here, aha, it's a real aha moment for almost everybody in the class. So I don't know exactly the best strategy, but I know that this might be an important part in how the sequencing of your storyline is important. On that point right there, what are your thoughts? what would be your approach if you wanted to consider this kind of spontaneous electrochemical cell and use that to illustrate standard and non-standard conditions?